Am I on? Can you hear me back there? Okay. Great, so I think we'll get started today. So thanks for joining me here today at the Open IoT Summit Workshop. This is my, I think, third time speaking at a Linux Foundation event or Node.js Foundation event. And I always get a kick out of these kind of events because I come from the industrial automation space, and so a lot of the technology that we present at these events is totally new to the developer community. And it's really cool to see a lot of the new ideas that the developer community, the Linux community comes up with when they look at the technology that we work with. And so one of the prevailing themes or ideas out there right now that just about everybody and their sister is talking about is this whole Internet of Things concept. And that's what we're going to be focusing on today. Now, a lot of people talk about the Internet of Things. If you're from Germany or you talk to folks in Germany, they're talking about Industry 4.0. If you're the industrial space like I am, we're talking about the industrial Internet of Things, but they're all basically the same thing, and there's a lot of activity around it. So to start us off, I thought I'd kind of walk us through some of the applications that I'm seeing come out of the Internet of Things right now, because there's a lot of cool stuff going on. So for example, this is a smart connected refrigerator. This is an absolutely amazing piece of technology. 10 years ago, this would have cost an absolute fortune, but today you can pick one of these things up for the small price of about $4,000 to $5,000 at just about any Best Buy. The thing's absolutely amazing though, especially for that price point. It's got all kinds of sensors built into it. It's got internet connectivity built into it. It's talking to the cloud and doing things like predictive analytics on when you're gonna run out of milk to make sure that you always have milk for your cereal in the morning, which is an absolutely amazing thing. This particular smart refrigerator though, and I'm sure everyone here has seen the commercial for it, it takes it a step further. It has an IP camera built into the refrigerator, which is a great feature, right? Because if you're at the supermarket and you can't remember if you have eggs in your refrigerator, you can pull out your smartphone, open up the app, log into your refrigerator, and actually see in real time what's going on inside your refrigerator, which is great because sometimes your vegetables don't get along with your fruits. You got to get in there. You got to break the two up before somebody gets physically hurt. But absolutely amazing technology. This is another one I've seen a lot about. This is the smart connected barbecue. This thing is absolutely amazing as well because it's a really good idea to be able to light your barbecue when no one's around. Like let's say I get home, I feel like having a barbecue. At the airport, I can open up my app and I can start the fire when no one's at home in my house. But the point is, it's absolutely amazing technology, right? Not necessarily a good idea to start a fire when no one's around. This one, though, I picked one of these up. I just found out recently that I'm going to have my first baby, so I'm pretty excited about that. But I thought I'd get in shape, you know, drop a few pounds, picked up one of these things, connected it to my home network, installed the app. The thing is an absolute spam machine. It direct messages me on Twitter, it endorses my LinkedIn profile, it likes posts, it sends me all kinds of notifications about dietary supplements. It's an absolute spam box. But when we take a step back and we look at this Internet of Things technology, it's absolutely amazing stuff, right? We've got smart connected scales, we can light fires when nobody's around and hopefully not burn the house down, and we can see what's going on inside our refrigerator from wherever we are. So let's stop right there, because that is not what we're going to be talking about today. Definitely not consumer level devices. There's a lot of buzz around the whole Internet of Things concept, IoT, but I think we're missing a much bigger opportunity. And that's what we're going to be focusing on today. So we're going to be talking about taking a lot of the technology that the Linux community is familiar with, like maker boards and open technologies and standards, and we're going to talk about how we can apply those pieces of technology to industrial grade systems and what value we might be able to get out of doing that. Because I think that's how we're going to build the real Internet of Things, or at least the real Internet of Things that I think the majority of us want to actually get to. So my name is Matt Newton. I'm the Director of Technical Marketing for an industrial automation company named Opto 22. We have a booth here at the show. We're the ones with the big white wind turbine, if you haven't seen us yet, spinning around. And we're going to talk a little bit more about that today. But three key ideas we're going to cover today is I think there's a much larger opportunity out there that we can all start tapping into. We're going to talk a little bit about the differences between industrial systems and consumer systems from a design perspective, from a technology perspective, from an application perspective. Because while there are some similarities and a lot of opportunities for getting more value out of these types of applications, there's some pretty big differences also. And then finally, we're going to get into the nitty-gritty on what I think the developer community needs to actually start porting some of this technology over so that we can get more and more value out of these kinds of applications. So to make sure we're all on the same page, because I come from the industrial space, a lot of people are here from the Linux space or the open source space, I thought we should get on the same page about a few definitions. Because people throw around this term, Internet of Things thing all the time. But what the hell is an Internet of Things thing? What exactly is it? It's such a nebulous term. But if you look at it and you boil it down, and yes, I do realize that the Nest thermostat shows up in every single IoT presentation, but there's a good reason for that. If you boil it down, IoT devices, all of them have three key and very important characteristics built into them. They have the ability to sense the world around them. They communicate using standard internet protocols, maybe even programming languages, and they have the ability to control something in the real and physical world. So they sense, they communicate, and they control, just like that Nest thermostat. So it's installed in my hallway. I have one of these things. I love it. I paid way too much money for it, but it's still a very cool piece of gadgetry. But it's got some sensing built into it. It knows if I'm in the house with its motion sensor, if I walk past it. It's got a temperature sensor built into it. And it uses that information to communicate over the internet, to talk to the Nest cloud and figure out what temperature does Matt like the house set at. And if it figures out that the temperature is outside of that set point that I've configured, it performs some type of control. So it'll flip on my air conditioning system or my heater using an electrical signal. So this technology is out there. We're using it all over the place today. But that's an Internet of Things device, at least for this presentation. It senses, it communicates, and it controls something in the real world. So what is a legacy device? And we'll get into why legacy devices are the massive brownfield opportunity that's in front of us all right now that we can tap into. A legacy device is something that's been installed for years and years, probably decades. Think about how long we've been building, shipping, and installing devices that are powered by electricity. So there's all these things that are out there. They're sitting there. They still have a lot of value built into them. They're probably still performing the tasks that they were designed for, but they were designed, rolled out, shipped way before this whole Internet of Things concept came about. So they don't have connectivity built into them. No internet connectivity, but there's still a lot of value in them. So third definition, what is a control system? Does anybody in here know what a control system is? Industrial control system? Feedback's a good one. But let's keep it simple for the purposes of the presentation. So if you think about your car, when you're driving down the road, you hit the desired speed that you want your automobile to travel, you push the button on the side of the steering wheel, and the car's cruise control system takes over. Now, the system inside the car is going to monitor how fast that car is traveling, and if it gets above or below the configured set point or speed that you want the car to travel at, it controls some type of input, right? So we apply the gas to speed up, we apply the brakes to slow down. That's the basics of a control system. We configure a set point, and then it runs to make sure that that set point stays where it's supposed to. And if it doesn't, it does things to take over and bring it back to that set point. So control systems are used all over the place. This building right now has a control system to run the HVAC system. We use them in manufacturing, we use them in process control. We use them for cool stuff like making beer, running nuclear power plants. They get used all over the place. We've been shipping stuff like this for years and years and years. Okay, definitions out of the way, that's the boring part. Let's get back to the fun stuff, the maker boards. So recently, I started screwing around with Raspberry Pi boards, and they are super cool. The amount of computing power in these things is absolutely amazing. So originally, they were designed for software education. They're making inventors and tinkerers out of just about anybody that has $35 to pick up a Raspberry Pi. Personally, I have one at work. I used to be in the IT space, so I screw around a lot with trying to break into our wireless network at work, because that's fun for me. That's what I like to do. I was amazed that this thing actually has a full-blown Kali Linux, security penetration testing distribution available for it that I could just download, slam on it, and go. So lots of cool things going on with the Raspberry Pi and the maker board community. I saw this one on the internet. I thought it was funny. It's an automated dog watering system, which is great. Make sure Fido's always got fresh, clean water available, all powered by, I can't remember if it was a Pi or an Arduino. But this is another one that I thought was pretty cool. and kind of goes along with what we're talking about today. So to date myself, and I can't believe I'm already at the point where I have to worry about dating myself, that's a Game Boy video game system. So I had one of those when I was a kid. Of course, it's long since died. It's probably in a landfill somewhere. But this person took their old legacy piece of video game equipment with a Raspberry Pi, just basically breathed new life into that old piece of equipment, all using new computing technology. And that's kind of what we're going to be talking about today. Again, going back to the bigger opportunity. So I have to ask myself, we've got like 10 million Raspberry Pis that have shipped, and that's just the Pis. I think they're probably closer to like 11 million by now. But if you think about all of the engineers out there, the talent, the software engineers, the hardware engineers that are out there, you know, having a blast, putting together automatic dog watering systems, I gotta wonder if that huge pool of talent, if we took it and we directed it at much larger scale applications, maybe industrial applications, what kind of value could we get out of doing that? Now, to illustrate my point, and remember we're an industrial automation company, I thought I'd walk us through a quick case study. And this one was pretty cool. As soon as I found out about this story, I got incredibly jazzed because I've been waiting for people to start doing this kind of stuff for 5 or 10 years. It all starts around California's green grid. Now in California, if you take a trip back in time with me, say 30 or 40 years ago, pollution was a huge problem. Like my dad was growing up, he'd go outside, he'd run around, he'd play, he'd get in all kinds of trouble all day. When he got home at night, his lungs literally burned, like physically burned from all of the pollution that he breathed in throughout the day. So it was a pretty serious problem. The good news is that we finally got smart, and about 30 or 40 years ago, we started rolling out these green energy sources. So we have solar panels being installed all over the place. We've got a boatload of wind turbines that are out there generating electricity for us. And we've got a lot of hydroelectric dams that are out there, and if they survive this torrential downpour we've been experiencing without washing away, we'll keep getting juice from them. So today, we're pushing about 20% of our daily energy requirement coming from green energy sources, so it's a pretty great thing. The downside, though, is that it's fairly new technology. So there's a few hurdles that we haven't quite figured out how to get over just yet. One is that they're based on natural sources, right? So if the wind's not blowing, our turbines aren't spinning. If the sun's not out, our panels aren't generating electricity. So, you know, they're not always there when we need them. The other problem is that we've rolled out this infrastructure, particularly the solar panels, so quickly that there are times during the day when we actually generate more electricity than we need. And that can be a problem for the grid, and we'll get into that in a minute. But the crux of it is that the grid was designed for power transmission, not for power storage. It's basically one big circuit, right? So our grid is actually a pretty fragile system. We can't store that excess electricity, so what we do is we try to generate just the right amount of electricity to meet demand at any given point in time, because if we send too much electricity to the grid, you know, it's just like your Raspberry Pi. You send too much voltage to it, you melt stuff, blow stuff up, but this is on a much grander scale. So we're blowing up big pieces of industrial equipment, very expensive stuff. Now the flip side is when we don't have enough electricity, we don't have enough electrical generation assets spun up and running to meet demand, that's when we run into blackouts and brownouts, which is a bad thing too, right? When I was a kid, I thought it was the best thing ever, lots of fun, get out the candles and get to play with the matches. But if you think about hospitals and our infrastructure that runs off of electricity, we need that stuff to be reliable and running all the time. Now the crux of the problem, in California particularly, but it's across, you know, the entire country, the entire world, is that our demand for electricity fluctuates up and down all day. In the morning when we're all asleep, it's pretty flat. It's pretty easy for us to keep production where it needs to be to meet demand, but then we go to work and it drops. We got to figure out how to keep the grid in balance at that point. But then a really terrifying thing happens in the evening. Right about the time we're all excited and heading home after a long day of work, we go home, we flip on our big screen televisions, we crank up that air conditioning, no matter how much our wives tell us we're freezing, they're freezing. But basically in the short span of 2 to 3 hours, demand on the grid skyrockets very, very quickly. And the energy producers struggle to figure out how to dump just the right amount of electricity on the grid to keep it in balance at any given point in time. Now, in California, we have a cute name for this problem. We call it California's duck curve problem, because if you look at the slope of the supply and demand curve there, it kind of looks like the back of a very cute little duck, but it is not a cute little problem. So what do we do when we don't have enough electricity on the grid? Well, basically our utilities get on the phone to the energy producers and they say, hey, we need more juice, crank up that power plant, or flip the wind turbines back on and start sending more juice to the grid, because remember, we're trying to keep it in balance. What about when we have too much electricity though? And this is where the sad part of the story comes into play. So if you think about our existing power generation infrastructure, nuclear power plants, hydroelectric dams, natural gas power plants, these are massive install bases of lots of industrial equipment. It's not designed to be turned on and off with the flip of a switch. So it literally takes like an entire day, about 24 hours, to get one of these resources spun up to actually start generating electricity, or to wind them down so that they're not sending electricity. Now the sad part is that our green energy sources, like our solar panels, it's real easy to flip a switch and disconnect those things. So when we need to throttle back production, it's our green energy sources that are usually the first ones to get disconnected, which sucks because then we're not getting to use those green energy sources. Maybe we're polluting the environment more. It's kind of a problem. So it's a really difficult problem to figure out, and there's a lot of really smart people trying to handle it. In California, it's the California Independent Systems Operator. They're basically the utility for the state. These folks have an incredibly difficult job because literally what they're trying to do is predict the future. They're trying to look at all different kinds of data sources. How much power was needed last year? How many resources do I have spun up generating electricity right now? Where are my green energy sources at? What's the weather going to be like tomorrow? Can I count on my green energy sources? So they've got all these different feeds of data, and they're mashing them up using these massive supercomputer systems to try to figure out, what do I need to spin up or spin down to keep that grid in balance? So it's a pretty serious problem. Remember though, it's all about that circuit. We're trying to keep supply and demand in equilibrium at any given time. So one of the tools that CalISO has available to them is something called the spot price of electricity, which is just a clever term for a market price. So it's the amount of money per kilowatt hour they pay to our energy producers to actually make and distribute energy for us. Now, it's a market price, so it fluctuates based on demand and supply, just like any other price. So literally, this price will range, like in this case study, this particular customer, he was telling me that it would range anywhere from like $200 per kilowatt hour, right, when we really need electrical generation, all the way down to like -$200, $300, $400 per hour when we're real concerned about sending too much juice to the grid and blowing stuff up. So that's effectively a way that the CalISO can fine our green energy producers for sending too much juice to the grid at any given point in time. Now, these folks in particular had several turbines. They've got a big wind farm, lots of them out there. They were designed and shipped. I think they'd been out there for like 20 or 30 years. This person got into the market because they thought, you know what, I can make a living off of producing green energy. It's absolutely fantastic. So we rolled them out there. They've been out there. They've been running, operating. These are our legacy devices that we talked about. But when they rolled out this spot price of electricity, these folks started getting hit with like a $10,000, $12,000 fine every single day. They couldn't get to their turbines in time to turn them off. So literally what they were doing is they'd jump in a truck, they'd radio a technician would jump in a truck, and that person would drive around from turbine to turbine and physically switch the turbines off. And if they didn't get there fast enough, then they'd get hit with these massive fines. So imagine this, you're this person that got into this green energy space, you're hoping to make a living and maybe benefit the environment also. Yesterday, you didn't get to your turbines fast enough and you get slammed with like, I don't know, $9,000, $10,000, $12,000 in curtailment fees. And so you're starting to rethink, maybe I don't want to be in this green energy space anymore. Maybe it's not something that I can make a living at. That's kind of a downer. And remember, these things are rolled out what I call back in the dark ages, before the internet, because as long as I can remember, the internet existed in some way, shape, or form. These are not smart turbines. Remember, there are legacy devices, not a lot of brains built into them, and they're designed to be controlled literally from the physical world. So you physically have to go up to them, flip a switch to turn them on, flip a switch to turn them off. So what's our green energy producer supposed to do here? Let's think about that Internet of Things device definition again. It senses, it communicates, and it controls. So we're sensing the world around us, we're communicating up with the cloud, and we're doing some type of control, just like that Arduino board could do, right? Just like a little maker board can do. What if we took that type of technology, those ideas, those concepts, and we applied them to our wind turbine? Because it's got some of that stuff already. It's got some sensors built into it, so it knows, how fast the wind's moving, what direction the wind's coming from. It can change its blade pitch and move its head into the wind to generate the most electricity possible. So it's got a control system, and it's got that sensing capability built into it, but it's missing that communications piece, which is critical for us to actually start building this Internet of Things that everyone keeps talking about. It needs communication. So what would happen to that legacy asset, that turbine, if we actually added some type of IoT technology to it? What would happen if these things actually started talking to various cloud applications? They could bridge the physical world that they live in right now and the digital world, and that's exactly what these folks did in this case study. They dropped a new control system into it that had internet connectivity and communication capabilities built into it, and now these turbines are literally smart enough to peer into a cloud computing system, the digital world, and figure out what they should do in the physical world. Should I turn on? Should I turn off? What's the spot price of electricity on the website that I need to check to figure out if I should do that? And these things jumped in value literally overnight when they rolled out this control system. So that's one cool thing that they did. We've got them smart, they're figuring out what they need to do automatically. The poor person doesn't have to run around from turbine to turbine to turn these things off. But these folks took it a step further. And this is where the real value, I think, comes in these IoT applications. So they took all the data that these things are generating from all the sensors that they have on them, and they're recording all of that and putting it into something that they call a turbine profitability report. So they've got all different kinds of turbines distributed throughout this wind farm, and they can figure out exactly which turbines are the most profitable to be running based on historical maintenance costs, current conditions, the model of the turbine. So they're literally maximizing profit based on the big data that these systems generate. So they've got all kinds of reports. They're doing predictive maintenance, predictive analytics. They're trying to replace parts based on things like bearing temperature before something actually goes out. And they've even got these things set up to do like alert notifications for service calls when something gets out of whack. That shouldn't be, like for example, if a bearing temperature gets much higher than it should be, these things will send an alert out and get an operator out there to fix it. So that's the real Internet of Things. Smart connected scales are great. Being able to look at your fruits and vegetables from your app on your phone is awesome, but I think this is the real Internet of Things we all want to get to, is actually getting data out of these legacy systems that are out there and figuring out how can we match that data up with other data sources to maybe predict a problem before it happens, to actually get more value out of those legacy assets, get these things connected to the cloud and talking. So that was one application that I was particularly jazzed about. So the maker community, the engineering community, the software development community, what are some other opportunities where they might be able to engage in these types of applications? So back in 2010, does anybody remember the Gulf oil spill? We dumped about 3.2 million barrels of oil into the ocean, totally screwed up the environment. A whole bunch of people died. The rig caught on fire, sank to the bottom of the ocean. Now, as somewhat of a technology dork, I look at this kind of stuff and I wonder, if there was some cloud analytics package looking at that rig, could it have figured out that, all those previous evacuations that had to happen, all the safety issues that were going on, if we could have collected that data and then in the cloud, through some analytics package, compared it to other rigs that were out there that maybe had, a lower number of safety incidents, could we have identified a pattern where we might need to change something on that oil rig before something very bad happened? All through the data that it generates, all through cloud analytics. That's the kind of stuff that I think we have to start thinking about as the developer community and the industrial space, all of us. So that's another application. How about city infrastructure? This one is such a no-brainer to me. Flint, Michigan, right? We dumped a boatload of lead into the city's water system. A whole bunch of kids got sick. What if there was a sensor in the water that was reporting data up to the cloud, and that cloud system was comparing it to other city infrastructures? What if it could have identified, the lead level in that water is way, way higher than it's supposed to be right now compared to all the other data sources that I'm gathering. How many kids wouldn't have gotten sick if we could have prevented that? That's the kind of stuff that I'm thinking about, that I'm talking about. What about manufacturing applications? I got into the tech industry just as we started offshoring a ton of manufacturing. It was all going offshore because cost of labor was cheaper, whatever. What if in the US we could cut costs in manufacturing? What if we could identify ways to decrease waste by applying this type of technology? What if we could make manufacturing here more competitive? Maybe we could create more jobs. More jobs is always a good thing, right? So those are some of the applications. But the big opportunity that we're talking about here, at least from a technology perspective, is we want to bridge the physical world, literally the world where our legacy devices live, like our wind turbine. We want to bridge that world to the digital world of cloud computing, software as a service, application platforms as a service, because we have almost infinite computing resources up there. We just need to get our systems that are already out there, all the legacy equipment, the sensors, transmitters, closed loop control systems. If we can get that stuff cloud enabled and actually communicating, I think there's a lot of value to be had in that. So if it was super easy, we would have figured out how to do this already and we'd already be doing it. I wouldn't be up here. So there's a significant challenge in front of us actually getting this done. Now, the biggest challenge that I've seen is that it's really kind of a twofold problem. There's a massive technology gap between the industrial world and the world of the maker community. Now, on the industrial world, this is literally where physical value creation takes place. This is where we wire up electrical loads and actually do something in the real world. We switch electrical loads to make hardware that builds other hardware. We produce electricity. These are applications that have been in place for a long time. A lot of the technology that was installed for these applications was designed for that specific application, which means oftentimes it's proprietary, which means it's very difficult to interface those types of systems with other systems. For example, our cloud-based analytics packages. But this is where our sensors, our motors, our pumps, all of our legacy devices actually live. Now, if we contrast that with the maker community, these folks live like in the software development, information technology space. So they're constantly thinking about how can I get systems to intercommunicate better, faster? It's all about data. How do I get access to more data? How do I move the data faster? Now, because of that, a lot of the technology here, it's open technology a lot of times. So we have like TCP/IP so that we all know how to talk to each other, right? We have HTTP so that we all browse the web the same way. Lots of technology that's all designed to talk to each other based on this whole open standards philosophy. But remember, what we're trying to do here is get all the big data. When we talk about big data, we're talking about big data from our legacy devices. We want to get access to that information, push it up into our cloud analytics packages or whatever it is, whatever IT system, try to figure out how we can improve the world by pushing changes down into our legacy devices, just like we did with those wind turbines, right? We started getting access to their data. We started figuring out how can we improve how they're functioning based off of that big data, and we made a change to improve how they were operating. That's our objective here. The other problem is that there's a huge cultural gap here as well. In the industrial world, hardware gets installed and then it doesn't get touched for like 10, 20, 30 years, right? It's that adage, if it isn't broken, don't fix it. So a lot of times firmware never changes, software never changes. That's why in the industrial space, we have incredibly long product life cycles that have to last a long time. Grossly different than the maker community, right? We've had how many revisions of the Raspberry Pi in the past like 3 or 4 years? I think we're on version 3 or something like that. So things don't change over there very often, but they change all the time on the maker side. So some of you out there might be thinking, at least I hope you're thinking at this point, why not use a Raspberry Pi? And that's a great idea, because you know what? Raspberry Pis are freaking awesome little pieces of technology. You can prototype with them incredibly quickly. They're really easy to learn. Remember, they were designed for education. They're super cheap. I can't believe how much computing power you get for $35 these days. It's incredible. They're readily available. I can have one here probably by the end of the day if I absolutely had to. They've even got some GPIO built into them. So you've got a few pins on there where you can actually pull sensor data in, figure out what you want to do with it, maybe even turn something off with that GPIO pin. And they've even got an SD card for storage. So whatever software tools you like or whatever Linux distribution you like, port it over to that SD card and get your Raspberry Pi up and running with the tools that you're used to and you like. How about some reasons why we might not want to use a Raspberry Pi? And if you haven't noticed the flamethrower coming off the rig there, that's exactly where we're going to install your Raspberry Pi. Now, the industrial world is a vicious and frightening place. There are all kinds of interesting characters that get pissed off when technology doesn't work and throw it underneath their tire and run it over. So the systems that get installed in these applications, they're incredibly rugged, they're incredibly tough, because these are mission critical applications. And remember, we're using high voltage in these applications, stuff that if you walk up to it and touch it, it'll kill you. It's not like 3.3 volt, digital I/O here. This is life or death mission critical stuff. So to combat those mission critical applications, there's a whole bunch of stuff that gets installed or developed into industrial systems, like I/O channel isolation, which is where if a piece of the control system blows up, it won't take down the entire rig. We have EMI resistance because we're switching really high loads of electricity. We've got file system recovery. So let's say your Raspberry Pi, for whatever reason, loses power. Are you 110% sure that it's going to boot up without some file recovery issue every single time? So my point here is that Raspberry Pis are super cool. They're great for software education. They're fantastic for prototyping. They're not necessarily designed to make sure the oil rig doesn't burn down. Because what's the real cost, right? What's the delta between that $35 Pi and that oil rig? If we catch the oil rig on fire, somebody might die. At a minimum, we're going to lose really expensive equipment that, would be a bad day for anyone. That's the real cost. So what is the solution then? Because going back to the opportunity size, it is massive. Remember, how long have we been shipping electrical devices? There is so much stuff out there waiting to be tapped into, right? If you look at my company, we've been around for, I think it's like 42 years now, 43 years, something like that. And we've been shipping these little I/O modules that basically do this, physical world to digital world conversion. What you do is you wire up something like a motor or a pump to one of these cards. Now the cards aren't a 1-to-1 ratio, which means we have some cards that'll do all the way up to 32 devices or 32 pumps, motors, whatever it is you want to talk to. Now if you multiply whatever number you want to pick, 1 to 32, by the number of modules we've shipped in that time, which is roughly over 100 million modules, it starts to give you some idea of the number of devices that are out there that are waiting to be tapped into. But if you take a much bigger approach, much broader approach, Opto 22, we're a fairly small company in that industry. We compete with massive juggernauts like Rockwell Automation, General Electric, Schneider, Siemens, multi-billion-dollar international conglomerates. Think how many devices they've shipped. But let's think about the bigger opportunity for a minute. Go back to Flint, Michigan and the oil rig. Those applications, those opportunities, we could literally start applying technology that could make the world a better place. So that's kind of what we're looking at here. Billions and billions of dollars, billions of devices that we could actually get out there, tap into, and start doing some cool stuff with. So how do we do it? How do we bridge that gap? Because like I said, there's that technology and that cultural gap that we've got to get over. Eventually, hopefully, the maker community will start migrating into the industrial space, and we'll start seeing more open standards and programming languages built into that kind of hardware. We've got to make the voltages and the currents of the real world, what those pumps, motors, sensors, relays, what those things speak. We've got to make that available to these cloud applications, which means we basically need to digitize it into things like REST APIs, HTTP, protocols and languages that the internet understands. Hopefully, industrial equipment will be designed from the get-go and shipped with that kind of stuff built into it, but it's going to take a long time. It's going to be a while. So in the meantime, what you need is some type of industrial Internet of Things platform. You need like a development platform that'll bridge the gap between the physical world and the digital world. Now, remember, it's got to be able to translate what the pumps, motor sensors, what those things communicate in to the digital world. And it's going to have to be super tough. Remember, when the operator runs it over with the truck, we don't necessarily want it to bring down the oil rig or whatever bad thing might happen. So it's going to have to be able to survive incredibly harsh environments. Going back to the billions of devices that are already out there, we're going to need a boatload of I/O built into this thing. And we're not talking like 3.3 volt I/O. We're talking about I/O that can switch huge loads of electricity, which is what goes on in the actual real world. And remember, we want IoT communications and programming capabilities because there's this huge pool of engineering talent out there messing around with maker boards. If we let them get access to this type of industrial equipment, what could they do with it? So we need to have a hardware platform that communicates and understands the languages that those folks are familiar with. things like Node.js, JavaScript. I've been at the booth all day, and as soon as I tell people that they can control a wind turbine with some JavaScript code, their eyes light up. It is the coolest thing I've seen in my entire career. The ideas that are flowing from people, it's just amazing. So let's say you're a die-hard Raspberry Pi person, right? You absolutely can't get away from your Raspberry Pi. Or maybe you want to quickly prototype something with a Raspberry Pi. And yes, this is my shameless product plug for the presentation. Let's just get it right out of the way. This is a Raspberry Pi daughter card. So basically, you take the Raspberry Pi, you drop it onto the daughter board, and then through the GPIO pins on the Raspberry Pi, you can control industrial-grade I/O modules and switch those high voltages, high currents, all from your Raspberry Pi. So kind of cool, something that's out there. We're testing it. But so to recap, if anybody wanted the slides for the presentation, they're available at that URL up there. Feel free to download them. The market opportunity here is massive. The tools are out there right now. Remember, the Nest thermostat is shipping today. This stuff, we can do it right now. We just got to get two very different groups working together. And I think it's going to be up to the developer community to actually start making this stuff happen. So thanks. That's all I had for everybody. Any questions? Questions? Anybody? I know somebody's got one. It always takes one person to get the dialogue going.
I guess, there's a level of the, just to throw it out there, because I mean, I was competing on some of the levels, but the Raspberry Pi as an entity, and a lot of the other type of, let's say, small computers in there, have not got the reliability built into them.
That's right.
And not being designed with the capacitors or anything else.
That's right.
To be able to do it. But on the other hand, I mean, I would agree with your thing of maker community. I think really is a learning community. And so it has been set up to get in there. But what is it, I mean, from your point of view, what does it take to bring in the reliability?
Well, that's where industrial specs come into play, That's why industrial equipment costs a lot more than a Raspberry Pi, as they go through all of those testing specification stuff. But without doing too much of a shameless plug, I can tell you there's already vendors out there in the market that are taking things like Linux and open standards, and they're applying them to industrial grade equipment. So that stuff is out there and available in the market today, and for not as much money as you might think. Other questions? Anybody?
So on that same issue, sensors and reliability, I mean, it takes a whole new world of thinking about. I mean, I don't know if you can speak about that.
It's the same kind of thing though. So on the consumer side, maybe like this building, right? The level of sensor that you buy to track temperature inside the building isn't going to be the level of sensor that you buy for making sure the oil rig doesn't catch on fire. It's the same kind of thing. It's all about risk, right? It's what's the associated risk if there's a failure, and it's much larger in an industrial scale, so you're going to pay for that. And there are a lot of different sensor companies out there in the industrial space, but again, you're paying like way more for that kind of stuff than you are for a consumer grade sensor. So hopefully at some point in time, we'll see the prices come down on the industrial stuff, and sensors will start getting rolled out all over the place.
But we might need 3 sensors instead of 1 sensor, a little bit of a decision.
Yeah, absolutely. You might have to choose whatever sensor you need for your specific application, if it's industrial or consumer, commercial, whatever it is. Yeah.
This is an interesting point, though. What you're getting at is that the maker community is tremendously agile and incredibly careless.
That's very true.
And run code on it that it does have. They don't want to try except me.
Sure.
I want to use one because I'm too busy getting from A to B. And again, talking about your oil platform on the middle of the woods, you kind of want that thing to be fail-safe.
You do.
So what's your?
You do.
Have you thought about how do you advocate for the maker community?
I don't know that it's so much an option anymore, and it will be for a certain amount of time. But a quick show of hands in here, who knows what ladder logic is? So we've got a few. Who knows what JavaScript is? There we go. So the developer community, the software engineering community, there's a shift going on. It's happening at an educational level. Like I talked to one guy today, he was a mechanical engineer, and he said he had one class all through college where they taught him any kind of like IEC languages whatsoever for the industrial community, like ladder logic or something like that. There's just a shift going on right now. And in fact, if you go to like I was at an industrial automation conference back in 2015, and they brought an education specialist in to talk about how we've basically like lost that group of people. We don't have people that are, highly paid HVAC engineers or industrial engineers anymore. Those type of schools are kind of going away somewhat in favor of, higher level, almost like theory level learning. So it's less about actually doing something and more, I guess, about like, talking about how it might be done. So I think there's a shift happening though.
Is price really a barrier for industrial IoT? I mean, because when you're talking about the scale of the problems, the cost of the hardware seems negligible anyway. So what role does maker hardware, does it matter?
Part of the problem that we're having, at least from my perspective right now, with this whole IoT thing and industrial Internet of Things, is a lot of people are struggling to figure out how to do a return on investment study on this stuff. Because you're applying totally new technology to a problem that has been alive and then we just accept it for a long time. So one of the things that people struggle with is, if I make the investment into some type of new technology, how long is it going to take for me to actually recoup my investment? Now, I'm not necessarily saying that maker board stuff should be deployed in mission critical life and death applications, but you know what a maker board is awesome for? Is prototyping an idea really quickly, right? Like that's what these hackathons are all about. We get a bunch of software engineers together, we throw them some boards, they hack together some stuff, and we figure out what technologies do we need to marry together to actually solve a problem. Now, if we did have Linux-based industrial controllers, which hint, hint, we do, and then if we had a bunch of Raspberry Pi makers in a room, trying to code up some application, then we could easily port it over to an industrial grade system. Does that kind of answer your question? Did I totally missed the mark there? All right.
I have several of these. I just dropped one in my pocket.
What is that?
Raspberry Pi 0. This is $5.
Yeah. So it's,
Same capability, a little slower than the $35 Raspberry Pi. 160 ohms. And the reliability is there.
it is. You're 100% correct. SD cards are awesome these days, but would you want to drop that $5 board on that oil rig?
Pretty easy to create a very inexpensive UPS.
Sure. I mean, you can get around it. It's just, how comfortable are you with the risk associated to it? That's what it comes down to. Any other? That's good.
I totally agree with you when you are talking about the prototyping phase, answering the question about hardware. And I agree with you when you're using your example about JavaScript and fast prototyping from a software perspective, like say hackathon. Don't forget that at hackathon type of things, people don't invest time on integration tests, and you invest so much, and
Sure.
you may have problem using interpreted languages like JavaScript and not compiled languages like others.
Sure.
When you gotta do like a very
You're at
industrial.
100% correct.
You cannot rely on runtime languages. That's the thing.
You're absolutely right. Absolutely right. So what if I had an API directly to the industrial I/O? What if I could program in C or whatever language you want, and I could talk to real-world electrical levels?
Yeah, I'm just saying that today, for reliability purposes, we have different examples where compiled languages save you a lot of troubles than
But I-
some languages that have really strong compilers, and it's really frustrating sometimes to go through that phase, but you know that when the software compiles, zero warning,
Yeah,
the software
that's good.
is almost
Fairly good, yeah.
fairly safe.
Yeah. But the whole idea here that I'm trying to convey is, let's give the developer community access to this stuff using the tools that's what I want to get to, because I think there's a whole bunch of cool stuff out there.
There is always a boundary that is very important.
You're absolutely right.
Because it's fun, you can do like really magic a few times, but
Yeah.
industrial is about like,
Yeah.
I'm still working with like industrial grade hardware and software, and people want like millions of dollars of liabilities.
Yeah.
I'm not like,
Well, that's what he was saying. That's what he was saying about the $5 board. It's just, it's your level of acceptance of risk. Is what everyone do.
would be happy to just keep that part.
Yeah, I mean, everybody wants margin, right?
Raspberry Pi is a
That's a great question. I don't know if this is the the theater for it though. Go ahead.
So your company builds that physical kind of gateway interface, but how much of the challenge is local control versus, like in the case of Nest, all the control happens in the cloud, the logic happens in the cloud, and that requires no hardware. It's completely software domain talking to a piece of hardware. So in that sense, from your perspective, from Opto 22, are the challenges really localized control, or are they about large-scale, potentially deep learning, AI kind of applications that can be done in the cloud to
Sure.
traditional systems that don't have really good control systems?
So there's two things there. There's this concept of edge computing, or people talk about, like Cisco talks about fog computing. Basically what we do is we take some intelligence and we push it down to where something's actually happening. And that's where the control system lives. Because it has to live there, because if the cloud's down and the oil rig catches on fire, we can't interrogate the cloud to see if we should perform the control to turn on the fire system. So you got to have some control and smarts down there at the edge level. But when we're talking about getting access to data from billions of legacy devices, we've got to have the IoT stuff, the protocols, the ability to program it with software developers. That has to start transitioning into industrial equipment if we're going to do this. So it's not, it's happening right now, but to get data from an industrial asset into like IBM Watson, today, I mean, it's not a trivial task, but there's things like Node-RED out there where you can wire together nodes, without even having to write a line of code and move data from the real world right into a predictive analytics system. So it's possible today. It's just that we're right at that point where we're starting to adopt this kind of stuff and do that kind of stuff.
Would you say that the challenges are large-scale controls, like large, like at a simple level, turning a switch on or off is a relatively simple action. Everyone would Raspberry Pi or Arduino has done that at some level. That's not the challenge. The challenge is when you should turn that on, when you should turn that off.
Yeah.
And is that there's a post from NASA a while back about, hey, who can come up with a better control algorithm to orient the solar panels on the space station? That's a challenge that you can run through simulation. Others means you don't have to touch the physical hardware, but the actual control system logic. That's a challenge. That's a real design problem. From Opto's or from your perspective and experience in the industrial field, how does that apply to developing kind of challenges?
Well, that's a good question. I don't have a good answer for you right now, but I'm getting the high sign back there. So if anybody else has any other questions or you want to talk about that further, swing by the booth or I'll be here after as well. Thanks, everybody. I appreciate your time.